Hey, my name is Parth Patel, and this is Lab 4 Circuits. Jumping into the introduction, we'll be using the loop rule and the charge conservation in addition to the steady state to predict the behaviors of circuits in series and parallel, and we'll be also calculating the potential difference within circuit components and examining the ohmic behavior, so like the Ohm's law with the resistors and capacitors. And we'll be doing this inside of a simulation. Some key physics topics and formulas we'll be using in this experiment will be the node rule, which basically says the total current that goes in must equal the total current that comes out. We'll also be using a loop rule, basically saying the potential difference is 0 if it's in a closed loop. We'll be also using Ohm's law, which is stated right there. And then the resistance is calculated for both parallel and series. A little bit differently, parallel is just a summation of each thing that provides resistance. And then in series, it's 1 over, so it's like the inverse. And then in this case, we're messing around with capacitors, so the formula for capacitor is down there as well. And we'll be manipulating it a little bit to solve for the potential difference right there. So these are a little preview of our results. We got the time constant to be 5.95 seconds. Ideally, it's at 6 seconds if you do it just hand calculations. And then in the experiment, we'll be charging a 10 ohm light bulb and a 20 ohm light bulb. And you can see the charge and discharge rates of those as well. So some assumptions slash model that goes with this experiment. The resistance of the wires and the amp meter is negligible, so we assume it's 0. And we assume the overall circuit is in a steady state because we're using an online simulation. And then the surroundings are everything that's not connected to the circuit, around the circuit basically. And then the system itself is the circuit only, and the components that are connected to the circuit. So this is part 1 of the experiment, which includes part A of the experiment, if you want to call it that, and part B of the experiment. So in part A, we're just connecting the amp meters in series together just to see what they read out and do hand calculation as well. So when you do the hand calculations, when you just add up all the resistors and then the voltage of the battery, you get 0.020 amps, which that's what it says on the amps as well. And the second one, we were supposed to disconnect one of the amp meters and then connect the voltmeter to it. You can see the voltage is 3 volts due to the batteries, but then the amp meter reads 0 because the voltmeter doesn't take any amperage to it. So this was part 2 of the experiment where we had to calculate the potential difference and basically graph it. So you can see on the left here, I did calculate each single component individually, and then due to the loop rule, everything does equal out to 0. And then graphically, you can also see the same thing with the first resistor, the second resistor, and then the amp meter in the series. You can see how it's slowly going off to 0 as how it started in the beginning. So this is part 2 continue as well. So we did the resistor calculation separately here. You can see it's off by a little bit. It's 48 ohms, 102 ohms. And then, of course, we assume the amp meter and the wires are negligible, so both of those are 0. But then, yeah, if you connect the amp meter parallel to the overall circuit, you can see that the current takes the most less resistance path to complete the circuit. So it goes through that, and the answer actually jumps to 0.6 amps, more than part 1, which was only 0.02 amps. So this is part 3 of the experiment where we use a capacitor and a light bulb to see its charge and discharge rate. So as you can see in this picture here, the light bulb does remain lit as it's charging up the capacitor fully. But once the capacitor becomes fully charged, as here, the light bulb dims. But theoretically, if you do remove the battery from the system, it will light up the light bulb like here. But once again, once it does become discharged, the light bulb will go dim. So in this experiment, we experimented with both a 10 ohm resistance light bulb and a 20 ohm light bulb as well. And then by hand, we calculated the time it took it to charge and discharge for both light bulbs. You can say it was around 15.8 seconds and 15.6 seconds and 26.5 seconds and 26 seconds. So part 3 of the experiment was using a 9-volt battery, a 0.2F capacitor, and a 30 ohm light bulb, and then plotting 10 seconds of it discharge to figure out its time constant. So using the potential difference and then using the ln of the potential difference over V0, the slope would give us the time constant. So when using the slope, which was negative 0.168, and then solving for the RC constant, we got roughly 5.95 seconds. And then the ideally case, if we just use the 30 ohms and then the capacitance, we'll get around 6 seconds. So some possible errors could have been round-off errors. The line of best fit on the graph was technically an approximation, and there could have been some timing-related errors with the input delay from the software and my reaction times as well. Answering the what if discussion questions. What if we used a real life battery and then a capacitor, no other resistor in the circuit? How would this affect the capacitor's charge? So the capacitor would charge up immediately in the ideal model, but would not be true in the real life due to the wires having resistance and the capacitor itself having resistance. So it would not charge up instant, but it would have high. And then answering the ammeter question. So if we use the ammeter in real life, it would have its own resistance, which would contribute to an overall low current as well.